after tubular reabsorption and secretion, it's important to consider water conservation. We need to be able to reabsorb a lot of water from the renal tubule. If you were to add up the amount of fluid that gets pushed out of all of your glomeruli into all of your nephrons each day, it would be somewhere between 150 and 180 liters of water. That's a huge amount of water. And yet, we only urinate about 1 to 2 liters per day. That's a lot of reabsorption that has to take place. Most of that reabsorption takes place in the PCT. About 65% of the water is reabsorbed there. But that still leaves a lot, about 60 liters or more, of water to be reabsorbed in other areas of the renal tubule. To help explain what's going on, I'm going to make a drawing of a nephron for you. Here's the glomerulus, with an afferent arteriole bringing the blood in, and an efferent arteriole carrying it back out again. Here we have the glomerular capsule, the PCT, the nephron loop with its descending limb and ascending limb, the DCT, and the collecting duct. We've already talked about a lot of what's happening here. We know that water and small molecules get pushed out of the glomerulus and into the capsular space that leads to the PCT. And we already talked about the fact that we do a lot of reabsorption here in the PCT. We're going to reabsorb nutrients like glucose and amino acids, ions like sodium and potassium and chlorine. We also end up reabsorbing some bad things like urea and uric acid. But those, of course, we can get rid of. We can put those back by tubular secretion. We also reabsorb, as I said before, a lot of water here from the PCT. We also reabsorb quite a bit of water from the nephron loop. To understand how the nephron loop is important for reabsorbing water, we have to understand how it creates a salt gradient. The nephron loop creates a salt gradient that allows us to reabsorb a lot of water by osmosis. This salt gradient is created by transport proteins here along the ascending limb of the nephron loop. Transport proteins along the ascending limb of the nephron loop transport sodium, potassium, and chlorine out of the ascending limb and into the surrounding fluid. This builds up a high concentration of ions outside of the nephron loop in the fluid of the medulla that's surrounding the nephrons. This is what we refer to as the salt gradient. As fluid comes from the PCT into the nephron loop and begins going down toward the medulla in the descending limb of the nephron loop, water is attracted to all of this high salt that's in the area surrounding the nephron loop. So water is going to be reabsorbed all along this descending limb of the nephron loop. Water is going to be pulled out of the nephron loop and into the surrounding tissues, where it can be picked up by the vasorecta capillaries that we find around the nephron loop. The fluid that originally comes into the nephron loop is not very concentrated. It has a relatively low concentration. But as it goes down this descending limb, the fluid inside the nephron loop gets more and more and more concentrated because all the water is being sucked out. By the time we get to the bottom, the fluid at the bottom has a very high concentration. It's very concentrated. Not very much water, lots of solutes. That's what makes it so easy for the transporters coming up the ascending limb to kick out all of that salt because it was very highly concentrated, so it wants to get out. Water does not leave the ascending limb because there are no aquaporins in the ascending limb of the nephron limb. The descending limb has lots of aquaporins, so water can get out, but not the ascending limb. As the fluid goes up the ascending limb, it gets less and less concentrated because we're pulling out all of these solutes. So by the time we get up to the top, we have a relatively low concentration to our filtrate. Once the fluid has reached the DCT, it's relatively low concentration, but we can see some water reabsorption here. We can reabsorb water from the DCT sometimes. We can reabsorb water from the distal convoluted tubule if antidiuretic hormone is present. If there's no antidiuretic hormone present, then water is not going to be reabsorbed from the distal convoluted tubule. And we'll get into the reason for that in just a little while. Once the fluid has gone through the DCT, it goes into the collecting duct. Now remember, the collecting duct, although up here at the top, has low concentrated fluid in it. The collecting duct goes down through the medulla. And the medulla has this high salt area in it because of the activities of the ascending limb of the nephron loop. As the collecting duct goes down through the salt gradient of the medulla, water is attracted to the solutes of the salt gradient, and more water is reabsorbed by osmosis. By the time we get down to the end of the collecting duct, where it's going to begin to drip into a minor calyx, we have a very highly concentrated urine. So we've taken all of the wastes and concentrated them into a very small amount of water so that we can get rid of the wastes without dehydrating.